Right, Neyman-Pearson Lemma. So the theory of hypothesis testing nowadays is referred as a classical or traditional method, as stated in Neyman-Pearson Lemma theory. So usually, we limit ourselves to test statistics, um, for which the probability of type 1 error is less than or equal to some constant alpha. So we want the minimum value of probability of type 1 error in our test statistics, right? So now, a critical region, right, for testing a simple null hypothesis, mu theta equal to theta naught, against the simple alternative hypothesis with theta equal to theta alpha, theta A, is said to be the best or most powerful uh, if the power of the test at theta equal to theta A is at maximum. So we want to have a maximum value of power of the test to indicate that the critical region is powerful, right? So in this topic, this is actually the last topic for chapter number 3. So the objective of this topic is to find the most powerful critical region, right? We want to find the most powerful critical region of the size alpha, right? So for mu null hypothesis, theta equal to theta naught, and alternative hypothesis theta equal to theta A. So based on the hypothesis statement here, we want to find the most powerful critical region at the size alpha for a simple hypothesis. So we cannot find the most powerful critical region for composite hypothesis, right? So no, before we start with the Neyman-Pearson Lemma, we need to understand some notation, some term. So first is notation, another one is simple. Another one is simple and composite hypothesis. So in Neyman-Pearson Lemma, we're going to use a likelihood function. So the likelihood function definition is if x1 until xn is a random sample of size n from a distribution with a probability density function fx theta, and the joint probability function of x1 until xn is denoted as L theta, which is the likelihood function. So the likelihood function, as we do in chapter number 2, if you still remember the maximal likelihood estimator, first we need to find the likelihood function. The likelihood function is a joint probability function for all sample, right? Another thing that we need to know before we start with the Neyman-Pearson Lemma is simple and composite hypothesis, right? So the definition, if a random sample is taken from a distribution with the parameter theta, right, a hypothesis is said to be a simple hypothesis if the hypothesis is uniquely specify the distribution of the population from which the sample is taken, right? So we need to have a unique value of that of a parameter in a distribution. So a composite hypothesis is a hypothesis that is not a simple hypothesis lah. So it does not have a unique parameter for a certain distribution. So now to differentiate between simple and composite hypothesis, let's look at the example. Example number 1, right? So we have x1 until xn is a random sample from an exponential distribution. We have n sample size with from a exponential distribution for a parameter theta, right? Is hypothesis, not alternative hypothesis, theta equal to 3, simple or composite? So to know this, first what we need to do is we need to know the PDF of exponential distribution. PDF of exponential distribution is fx equal to 1 over theta exponential negative x over theta for x is more than 0, more than or equal to 0. So under alternative hypothesis, theta equal to 3, so the PDF will be fx theta equal to 3, which is equal to 1 over 3 exponential negative x over 3, right? For x is more than or equal to 0. So because of we can uniquely specify the PDF under the alternative hypothesis, right? We have none parameter left in the PDF. So this hypothesis is a simple hypothesis, right? So we can specify all the value in the PDF, right? So now look at example number 2, right? So in example number 2, suppose that we have x1 until xn, right? Is a random sample from exponential distribution with a parameter theta. So is the hypothesis now alternative hypothesis theta is more than 2, simple or composite hypothesis, right? Again, we need to know the PDF of exponential distribution, which is fx equal to 1 over theta, right? 1 over theta exponential negative x over theta for x is more than or equal to 0. So under null alternative hypothesis, theta is more than 2, right? So it can be fx theta equal to 3, fx theta equal to 4, and so on, right? Until, because theta is more than 2. So we don't have a unique specified distribution, right? So this one is not a simple hypothesis, is actually a composite hypothesis, right? Because we don't have a unique specified value, right? We have a many value of that parameter theta, right? Now look at example number 3. Under example number 3, right? Suppose that we have x1 until xn, right? x1 until xn is a random sample from a normal distribution with mean equal to mu and unknown variance sigma squared, right? So we know we have the value of mu, but we don't know the value of variance, right? So the PDF for normal distribution is fx equal to 1 over 2 pi sigma squared, taking a square root here, then exponential negative 1 over 2 x minus mu divided by sigma and square. This is from negative infinity to infinity, right? And then the variance should be more than 0, right? And mean also can be either from negative infinity to infinity. So from For null hypothesis, alternative hypothesis, mu equal to 12, right? So the PDF will be fx mu equal to 12, and the variance still unknown, right? It become 1 over sigma 2 pi exponential negative 1 over 2 x minus 12 divided by sigma power of 2. So based on this value, we still don't have a unique value for sigma, right? So this is going to be, if you change the value of sigma, then the distribution will be, the value of that PDF will be different, right? So this is not a composite, not a simple hypothesis, it's a composite hypothesis, because we still don't have the uh, unique value, right? So that's how we differentiate between simple and composite hypothesis for the distribution, right? All right. For Neyman-Pearson Lemma, right? So now once we understand the likelihood function, how to get the likelihood function, and how to differentiate between simple and composite hypothesis. So now we can move to Neyman-Pearson Lemma. Right. Suppose that we have a random sample from x1 until xn. Random sample x1 until xn from a probability distribution with a parameter theta. So then if C is a critical region of size alpha and K is the constant such that likelihood function for theta naught divided by likelihood function for theta A is less than K, so it's said to be inside the critical region, which is the conclusion we will reject the null hypothesis. So in this function, right, it will be look like this. If you draw a normal distribution curve, right, let's say this is on the right hand side, right, for example, for the right hand side. So this is going to be your critical region, which is your C, right? C is critical region, and K will be inside the critical region, right? So we want to find the value of K, right? The critical value, right? So if you have another one, L likelihood function for theta naught, right, divide by likelihood function for theta A is more than K, is said to be outside the critical region, which is we're going to accept null hypothesis, right? So if you can draw the probability distribution curve, right? So let's say we have rejection area, which is your critical area, critical region, right? The K will be outside the value of critical region, right? So this is going to be accept null hypothesis. This is your criteria, decision criteria for critical region, right? So, all right, can you hear me? Can you hear me? All right. So then C is the best and more powerful. C is the best and most powerful critical region for testing the simple null hypothesis for null hypothesis theta equal to theta naught against the simple alternative hypothesis. So to find the critical region, using a Neyman-Pearson Lemma. So we need to make sure we have a simple hypothesis only. So if you don't have a simple hypothesis, you cannot fit into the formula and you cannot get the most powerful critical region, right? So if you have a composite hypothesis, you cannot estimate the real or accurate critical region because the value is not unique. The value of the parameter is not unique, right? So now look at example number 1. To understand this, we need to look at example number 1, right? So in example number 1, suppose that X is a single uh, observation, right? We have a single observation. So means that we only have X1, right? We don't have more sample, only one sample from our population with the PDF of theta x power of theta minus 1 for x is from 0 to 1. So we want to find the test with the best critical region or find the most powerful test with alpha equal to 0.05 for testing the null hypothesis theta equal to 0.3, theta is equal to 3, and alternative hypothesis theta equal to 2. So first step, solution. So how to do this? So first step, we need to check the hypothesis, right? So the null hypothesis is theta equal to 3, alternative hypothesis theta equal to 2, right? So since we only have one parameter in the PDF, so it will lead us to a simple hypothesis. So if we have a simple hypothesis, then we can apply. Neyman-Pearson Lemma, and to find most powerful test, right? So first step is this one. The second step is we need to find a likelihood function for theta naught and theta A. Theta 1. Theta naught means for null hypothesis. Theta A is for alternative hypothesis. Right. So L theta naught divided by L theta A, which is equal to, since we only have one sample, right? So the PDF is only one lah. So means we don't need to do a joint probability because you only have one sample. So this one is for 3x power of 2. 3x power of 2 means I substitute the value of theta equal to 3 into theta, and x theta minus 1. So should be 3x divided by power of 2 divided by 2x power of 1. Right? So if you can put this way, right? So it should be 3 minus 1, 2 minus 1 should be 3x power of 2, 2x only. Right? So then next step number 3. So 3x power of 2 divided by 2x is less than or equal to k, because we want to find the rejection area. Right? We want to find the rejection area first. So then it will lead us to 3x divided by 2 less than or equal to k. And if we bring others value to the right hand side. So x will be less than or equal to 2k divided by 3. So for this purpose, we know that 2k divided by 3 is critical value. It's a critical region, right? So this is your critical region. This is C. So we know that number 4, x is less than or equal to C. So this is going to be C, right? So now, how to find C? We need to find C, right? So number 5, so find C. So let alpha equal to probability of type 1 error, which is also equal to probability of reject null hypothesis when null hypothesis is true, right? So if the condition to reject null hypothesis is when x is less than or equal to c, right? When the null hypothesis is true, means the null hypothesis theta equal to 3. So this one should be theta equal to 3, right? So we know that the alpha is 0.05, right? As stated in the question, right? Alpha is 0.05. So this is going to make us easy to find the value of C. So to find the value of C, we need to integrate, because this is from for a distribution, PDF distribution. The range is from x 0 to 1. So this is from 0 to C, right? And the value of C is wait so the value of C is since we're going to use we want to integrate, so this one is going to be the PDF is theta x theta minus 1, right? So theta is equal to 3. So we substitute, this is with respect to x. So this is going to be, we input the value of 3 inside the theta. So it becomes 0 to c and 3x power of 2 with respect to x, right? So this one should be equal to x power of 3, right? From 0 to c, right? So you will get c power of 3. So this one should be equal to 0.05. So we need to find the value of c, right? So c is equal to 0.05. So 0.05 power of 1 over 3. So it should be equal to 0.368. So the value of C is 0.368. So from here, we can conclude that the rejection region of most powerful test for hypothesis, alternative hypothesis, theta equal to 3 versus, so this is null hypothesis, alternative hypothesis, theta equal to 2 is x less than 0.368. So this is a critical region that we want to find. So far, are you okay? Right. Can we move to the next example? Right. So now look at example number 2. So in example number 2, suppose x1 until xn is a random sample from a normal population with mean equal to mu and variance equal to 16. So we have n sample, mean equal to mu, and variance equal to 16. Find the test that with the best critical region, that is, find the most powerful test with a sample size n equal to 16. So from here, we know that the n will become 16. So, and the significant level, alpha is equal to 0.05. So test the simple null hypothesis. So we have a null hypothesis mu equal to 10 and alternative hypothesis mu equal to 15. So now we want to find the most powerful test using Neyman-Pearson Lemma. But the condition before we use the Neyman-Pearson Lemma, we need to check whether the hypothesis is simple or composite, right? So the PDF for normal distribution is 1 over 2 pi sigma squared, right? Exponential negative 1 over 2 x minus mu divided by sigma squared. So now we already know the value of sigma squared, and we also know the value of mu, right? So it makes this hypothesis as a simple hypothesis. So since this is a simple hypothesis, then we can apply Neyman-Pearson Lemma, right? So to apply Neyman-Pearson Lemma, we need to find the likelihood function for L theta naught and L theta A, right? So the L theta naught is L for mu equal to 10 divided by L mu equal to 15 less than or equal to K. So this is what we want to find the rejection area lah. So we want to find the rejection area. So now is our task is to find the likelihood function. So we know that the probability density function, right, for normal distribution is 1 over 2 pi sigma squared square root exponential negative half x minus mu divided by sigma range squared. So we substitute the value into the formula 1. Let's see, let me use another color. 1 over 2 pi sigma squared is 16, right? Square root exponential negative 1 over 2 x minus mu is equal to 10 divided by sigma is equal to 4 squared. So this one we will do a joint distribution, probability distribution. So it will power of 16, right? So divide by 1 over 2 pi 16 square root exponential negative 1 over 2 x minus this is mu is equal to 15 divided by 4, right? Power of 2, and everything power of 16, because you are doing a joint probability distribution. So if you want to solve this one, so this one should be 32 pi, right? 16 multiplied with 2, it should be square root of 32 pi, and this also same, it becomes 32 pi. So we can remove this value, right? We can remove this value, so it will become exponential negative 1 over 2, right? Then this one also we can simplify this one, right? We can take out 4 and 2 multiply together, right? It become 1 over, this is 16 multiplied with 2 is 32, right? And summation of, because this is only x minus 10 squared from I equal to 1 until 16 xi. So this one divide by exponential negative 1 over 32 summation of xi minus 15 power of 2 I equal to 1 until 16. So this is less than or equal to k, right? Right. So since we have a fraction of exponential, we can do because we have same base, right? So it become exponential negative 1 over 32, right? So summation of uh, from xi minus 10 power of 2, this is from I equal to 1 until 16, and then this is going to be minus summation of I equal to 1 until 16 xi minus 15 power of 2. So less than or equal to k, right? So now the equation become harder, right? We can solve this problem by expanding the square, right? If you expand the square, so it become exponential negative 1 over 32, right? And then this is a summation of xi squared minus summation of we have 20, right? Because 10 multiplied with 2 is 20, summation of xi, and plus with summation of 10 power of 2. So we don't need to do a summation. Yeah, we need to do a summation here because it will lead us 16 times, right? So this is the first, and we need to minus summation of xi power of 2 negative 15 minus multiply with 2 is 30 summation of xi, and plus summation of 15 power of 2, right? So this is the expand version, right? So from here we can vanish this one, right? X power of 2 minus x power of 2, and then this one will become 16 multiplied with 100 should be equal to 1600, and this one should be 16 multiplied with 15 power of 2 should be equal to 3600, right? So once we simplify, we can simplify this equation, right? Negative 1 over 32, right? Become negative 20 plus 30, it should be 10 summation of xi minus 1600 minus 3600, it should be negative 2000, right? Less than or equal to k. So then, once you have this simplified version, so still we have exponential on the left hand side, right? So what we need to do is we take a ln. This is step number 2. Step number 2, taking ln for both sides, because we still have exponential on the right and left hand side. So it become ln exponential negative 1 over 32 multiply with 10 summation of xi minus 2000, right, less than or equal to ln k, right? So this one should be equal to 1, right? So negative 1 over 32, right? 10 summation of xi minus 2000, right, less than or equal to ln k. So now we can move. We want to stay x on the left hand side and others value on the right hand side. So we move the value to the right hand side. So it become 10 summation of xi. So the notation are different now. So more than or equal to negative 32 ln k plus 2000, right? Because the value of negative here, we move over there, so the sign will be changed. So now this is our critical region, but not yet finished. But we can do, we can make it nicer, right? So since we have sample size n equal to 16, right? To get x bar, right? So x bar is summation of xi divided by n, right? So we want to make this side become x bar, right? So it will look nicer. So now we want to force this side to summation of xi divided by 16, right? So how to do that? So it will become, we will take 10 summation of xi divided by 160 more than or equal to negative 32 ln k plus 2000 divided by 160. So it's still the same result, right? So now if you cancel this one, right? So it become x bar more than or equal to negative 32 ln k plus 2000 divided by 160. So this is your critical region, right? This is your C. So now we can say that x bar is more than or equal to C. So that's how we find the critical region, right? So if you want to find the value of critical region, right? The value of C. So we know that this is a rejection area, right? Rejection region, right? So to find the the value of C, now look at this equation. The equation says that the significant level alpha is 0.05, right? So we can use probability type 1 error. So probability of type 1 error is equal to 0.05, which is our alpha, which is also equal to probability of reject null hypothesis when null hypothesis is true. So we're going to reject the null hypothesis when x bar is more than or equal to c, when the null hypothesis is true. So the true null hypothesis when mu is equal to 10, right? Mu is equal to 10. So is 0.05. So we have x bar here. So we can use the normal distribution function. Z is more than c minus 10 divided by, so the Z distribution is x bar minus mu divided by sigma over square root of n. C minus 10, right, when mu is equal to 10. And sigma is equal to, what is the value of sigma? Sigma is equal to 16, right? Sigma squared. So sigma square root of 16 over 16. Sample size also is equal to 16, so this one should be equal to 1, right? It's equal to 0.05. So we want to find the value on the right hand side, right? Because the probability of more than. So this is going to be 0.05. We want to find the value of C. So now it becomes 1.645, right? We can take out the bracket. This is 1.645 is taken from Z 0.05, right? So it becomes C minus 10 divided by 1, right? So now C is equal to 11.645. Right. So now the question asks us to find the most powerful test. They're finding two questions here. First, finding the best critical region. We already find the best critical region, which is C is equal to 11.645. And the second part is we want to find the most powerful test, which is the power of the test, right? We want to find the power of the test. So to find the power of the test, right, number 2, power of the test is equal to 1 minus beta, right? And then beta is equal to probability of type 2 error. Probability of type 2 error, which is equal to probability of accepting null hypothesis when null hypothesis is false, right? So the critical region, the rejection region is more than, right? So to accept null hypothesis, it should be probability of x bar less than 11.645, right? So this is 11.645. So this is acceptance region. This is rejection region, right? So when the null hypothesis is false, and the mu should be equal to 15, right? For null hypothesis, alternative hypothesis, mu is equal to 15. So this one should be equal to probability of Z less than 11.645 minus 15 divided by square root of 16 over 16. So this one should be equal to probability of z less than negative 3.36. So this one should be how much? This should be on the left hand side, right? Oh, not nicer. So the rejection region here, the region that we want to find is on the left hand side, so negative 3.36. So the value here is should be berapa? So what is the value?
Zero point zero zero zero
3.36.
0.0004.
0.0036 39, right? 3.36. Yeah, should be 0.00039, right? So this is only the type 1, type 2 error. So find power of the test should be 1 minus beta, should be 1 minus 0.00039. So it will become how much? 1 minus 0.00039.
0.961.
0.99961. Right. That's how we solve example number 2. Any questions so far? Right. If you don't have a question, then we can move to the next example. So now, I only have 5 examples. I try to my best to finish all the example, right? It should be very easy on this one. So example number 3. So let x1 until xn have exponential distribution with parameter theta, right? And null hypothesis theta equal to 2 and alternative hypothesis theta is equal to 1, right? Find the most powerful critical region of size alpha. So first we need to know the distribution of each sample. It have a exponential distribution with parameter theta, and the PDF of exponential is 1 over theta exponential negative x divided by theta. For x is more than 0. So this is the first step. Second step is we need to check whether the hypothesis here is composite or simple. Since we only have one parameter, so this is going to be a simple hypothesis, right? So step number 3, we need to find the likelihood function for L theta naught divided by L theta A less than or equal to K. So theta naught theta naught divided by L theta A, it should be 1 over. So for theta naught, theta is equal to 2, and for theta A, theta is equal to 1. So this one should be 1 over 2, right? Exponential negative x over 2 power of n divided by 1 over 1, right? Exponential negative x over 1 power of n. So it become 1 over 2 exponential negative summation of x divided by 2 divided by, this is power of n, and this is 1 power of n, 1 over 1 power of n exponential negative x summation of x. So we can simplify this one, should be 1 over 2 power of n exponential negative summation of x divided by 2 and divide by exponential negative summation of x less than or equal to k, right? So we can do a simplification for this one, right? So it become 1 over 2 power of n exponential negative summation of x divided by 2 plus, because we bring this value up, so summation of xi less than or equal to k. You can do a simplification lagi, right? So it become 2 negative n exponential negative summation of x divided by 2 plus summation of x less than or equal to k. So since we do have exponential on the right, on the left hand side, so we can take ln to simplify, taking ln for both sides. So ln ln 2 power of ln 2 power of n negative n exponential negative summation of x divided by 2 plus summation of x, right, less than or equal to ln k. So it become negative n ln 2 plus summation of, so plus, do you have negative over there? Yeah, we when we solve this problem, right? Negative x, negative one summation of x divided by 2 plus summation of x, we will become exponential summation of x over 2, right? So if you do simplification, negative 1 over 2 plus 1 should be 1 over 2, right? So it become x over 2 less than or equal to ln k. So we bring others value on this value to the left right hand side. So summation of x divided by 2 less than or equal to ln k plus n ln 2, right? So then summation of x less than 2 ln k plus n ln 2. So this is your new critical region C, which is C. So summation of x is less than or equal to C. Okay, done. Now, we look at another example. Can we look at another example? You done here? You okay here? Right? So example number 4. So now, don't worry. Later I will upload this video into YouTube. Right. Example number 4, second last example, and then we move to the example number 5. Then we finish. So this is a very long example. Right. So example number 4. A random sample of size n from a normal population with sigma squared equal to 1 is used to be it is to be used to test the null hypothesis mu equal to mu naught against the alternative hypothesis mu is equal to mu1, where mu1 is more than mu naught. So use Neyman-Pearson Lemma to find the most powerful critical region of size alpha. So we don't know the value of alpha, right? So to solve this one, same procedure. First, we need to look at the null hypothesis, which is mu equal to mu naught. The alternative hypothesis, mu equal to mu1. And we know sigma is equal to 1, right? And n sample size and alpha is your level of type 1 error, right? So the PDF for normal distribution is fx 1 over 2 pi sigma squared exponential negative 1 over 2 x minus mu divided by sigma squared. So mu naught is some constant value, right? Some constant, and the sigma squared is equal to 1. So it satisfies all the value in the pure probability density function. So then this is what we call as a simple hypothesis, right? So step number 2, this is step number 1. Step number 2, we need to find the likelihood for mu naught divided by likelihood for mu 1. So the likelihood for mu naught is 1 over mu naught is equal to mu naught 1 over square root of 2 pi, and since variance equal to 1, so we don't need to mention variance. So exponential negative 1 over 2 xi minus mu naught squared. So this is power of n, right? So initially we do like this lah. We do a joint probability distribution, right? So it should be joint probability from 1 until n. So it become power of n lah, right? So divide by the same procedure. So the joint distribution, 1 over 2 pi sigma exponential negative 1 over 2 xi minus mu1 squared, right? So we can remove these two value because this is a two same value, right? This is less than or equal to k. Right. So the next procedure is so since we're going to multiply to the n this exponential, this value, right, it will become exponential negative 1 over 2 summation of xi minus mu naught power of 2 from I equal to 1 until n. So this one divide by exponential negative 1 over 2 summation of I equal to 1 until n xi minus mu 1 power of 2 less than or equal to k. Right, you can simplify this one. So it become exponential 1 over 2 summation of, this is negative 1 over 2 xi minus mu naught squared. This is plus 1 over 2, right? Summation of xi minus mu1 power of 2 less than or equal to k, right? So we need to do expansion for this one, right? So it become exponential negative 1 over 2, right? Summation of xi squared minus 2 summation of xi mu naught plus mu naught squared, right? Plus 1 over 2 summation of xi squared minus 2 summation of xi mu1 plus mu1 squared, right? Is less than or equal to k, right? So we can remove this one and this one, right? So it become exponential negative. So summation of xi. We need to do a simplification, right? So it become n mu naught squared divided by 2 minus summation of xi mu1 plus n mu1 squared divided by 2 less than or equal to k. So you need to do some simplification in this step. So after you do a simplification, right, for this step, it will become exponential n over 2 mu1 squared minus mu naught squared plus, right? So I just combine these two together, right? Summation of xi, right? Mu naught minus mu1, right? Less than or equal to k. So I think the value of negative here, it should be negative, right? Okay. So step number 3. So this is step number 2, and step number 3 is, since we have exponential on the left hand side, we taking ln for both sides, right? Ln for both sides. So we got ln ln exponential n over 2 mu1 squared minus mu naught squared minus summation of xi mu1 minus mu naught, and then this is ln k, right? So it become n over 2 mu1 squared minus mu0 squared minus summation of xi mu1 minus mu0 less than or equal to ln k. So we bring others unimportant value to the left hand side. So it becomes summation of xi mu1 minus mu0. So less than or equal to ln k minus n over 2 mu1 squared minus mu0 squared. So negative summation of xi should be ln k minus n over 2 divided by mu1 minus mu0, right? So you can bring the value, this negative sign, right, to the right, right? So becomes summation of xi more than or equal to ln so this one become negative, this one become positive. Let me rearrange this one. Should be n over 2 mu1 squared or minus mu0 squared minus ln k divided by mu1 minus mu0. So now if you want to change this sign to x bar, so x bar is equal to summation of x divided by n, right? So if you want to change this one, you need to multiply with n, right? So summation of xi is equal to n x bar, right? So it become n x bar more than or equal to n over 2 mu1 squared minus mu0 squared minus ln k divided by mu1 minus mu0. So we can leave x bar alone, right? N over 2 mu1 squared minus mu0 squared minus ln k divided by n mu1 minus mu0. So this is your critical region.
Sir, sir, sir.
This is our final answer. Okay, right. Done. Can we move to the next example, which is the last example for today, and we conclude the chapter number 3, hypothesis testing. So once we finish chapter number 3, you should expect test number 2, right? It will cover from chapter number 2 and chapter number 3. Right. So now look at example number 5, which is the last example for this lecture. Right. Suppose that we have a random sample of 4 observation, right? 4 observation, which is n equal to 4, and the density function lambda power of x exponential negative lambda divided by x factorial for x is from 0 to n, right? 0 to n, right? So now the question asks us to find to use Neyman-Pearson Lemma, right, to find the form of rejection region, right, for the most powerful test null hypothesis lambda is equal to lambda naught, and alternative hypothesis lambda is equal to lambda 1, where lambda naught is greater than lambda 1, right? So to do so, first, first what we need to do is to know the null hypothesis and alternative hypothesis, whether this is a simple or composite hypothesis. So the PDF fx is equal to lambda x exponential negative lambda divided by x factorial. So based on the PDF, you only have one parameter, right? So the parameter is lambda. So this is a simple hypothesis, right? So we can input the value, right? So step number 2. Step number 2, we want to find lambda, likelihood for lambda naught and likelihood for lambda 1 less than or equal to k, right? So this one, we have n equal to 4. Based on the equation, we have only 4 observations, right? So the likelihood function for lambda naught is lambda naught xi x power of xi and exponential negative lambda naught divided by xi factorial. So this is power of n divided by lambda 1 xi exponential negative lambda 1 divided by xi factorial power of n less than or equal to k. Right, so since n is equal to 4, so we need to substitute the value of n into the likelihood function. So, right, so lambda naught summation of xi, where I equal to 1 until 4, right? Sorry, lambda is, so x is from 1 until 4, sorry, 0 until 4. So summation of I from 0 to 4 xi. And then this is lambda naught, and then exponential negative 4 lambda naught divided by product of xi factorial from I equal to 1 until 4. This is for the first one. The second one is lambda 1 summation of xi. I is from 0 to 4. This is 0 to 4, right? Which is actually from 1 to 4 lah. Exponential negative 4 lambda 1 divided by product of I equal to 1 until xi, until 4. So for this one, we can remove the product value, right? Because it's the same. It's less than or equal to k. So next, it will become since we have the same base for lambda naught and lambda 1, so lambda naught divided by lambda 1, right? Power of summation of xi exponential negative 4 lambda naught plus 4 lambda 1, which is k, right? So since we have exponential on the left hand side, we take ln for both sides, right? So ln lambda naught divided by lambda 1 summation of xi exponential negative 4 lambda naught plus negative 4 lambda 1 less than or equal to ln k. So this one should be summation of xi ln lambda naught divided by lambda 1 minus 4 lambda naught plus 4 lambda 1 less than or equal to lambda k. So if we bring all together on the right hand side, so it should be summation of xi less than or equal to ln k plus ln 4 ln lambda 4 lambda naught minus 4 lambda 1 divided by lambda naught over lambda 1. Right. So as with previous example, if you want to change this one to x bar, it becomes n x bar less than or equal to ln k minus 4 lambda naught minus 4 lambda 1 divided by lambda naught over lambda 1. So it becomes x bar less than or equal to ln k minus 4 lambda naught minus 4 lambda 1 divided by 4 multiplied with lambda naught over lambda 1. So this is your critical region. This is your K, your critical region. So we know that from here, x bar should be less than or equal to C. Right. So this is the first part of the question. Right. So the second question for this example, by using the best critical region obtained in A, so we already know the best critical region, which is x bar less than C, right? Determine the value of K, the value of C actually, the value of K, if lambda naught is equal to 20 and the probability of type 1 error is 5%. So from here, the question says that this is the K, right? This is K. In the question, they say that this is K, but our understanding this is a C, right? It's okay, nothing to worry, right? So the next question is we want to find the value of K, right? Or the value of C. So this one should be, we know that alpha is 0.05 and lambda naught is equal to 20, right? So by using the probability type 1 error, probability type 1 error, which is equal to probability of reject null hypothesis when null hypothesis is true, right? So null hypothesis true is when lambda naught is 20, reject null hypothesis when the x bar is less than k. So we want to find the probability of x bar less than k and lambda naught is equal to 20. So this is equal to 0.05. So since this is not a normal distribution, but this is a Poisson distribution, right? Since lambda is more than 5, so we can use normal approximation, right? So still remember in QMT 161, normal approximation to Poisson distribution, right? So this one, when we use a normal approximation, x bar should be a normal distribution with mean equal to lambda and variance equal to lambda over n, right? So this one should be the z distribution should be x bar minus lambda divided by square root of lambda over square root of n, right? They will lead to a standard normal distribution, right? So since lambda equal to 20, so x bar will be normal distribution with lambda is equal to 20 and variance equal to 20 over 4 because we only have 4 observation, right? So now probability of x bar less than k is equal to 0.05. So probability of z less than k minus 20 divided by square root of 20 over 4 is equal to 0.05. So by using a normal approximation. So we are finding the value on the left hand side, right? So probability of z less than k is on the left hand side. So this is 0.05. So we want to find this value k. So based on z 0.05, it should be equal to negative 1.645 equal to k minus 20 over square root of 20 over 4. So now from here we can know the value of k is equal to 16.3217, right? Right. Are you okay? So the last question is, if lambda is equal to 16, compute the power of the test. So to compute power of the test is very easy. It's based on type 2 error. So number 3, power of the test is equal to 1 minus beta. So beta is equal to probability of type 2 error. So which is equal to probability of accepting null hypothesis when null hypothesis is false. So for here, we want to find the probability of x bar more than 16.3217 given that lambda is equal to 16, right? So we can use a normal approximation because the lambda is more than 5. So it becomes probability of z more than 16.3217 minus 16 divided by the lambda is 16 over 4, right? Should be equal to probability of z more than 0.16. It should be equal to 0.4364. So this is the probability of type 2 error. So the power of the test, is not very large because 1 minus 0.4364 is equal to 0.5636, only 56%. So it's not very good, but it's okay. We understand something here. I think they will conclude our lecture for Neyman-Pearson Lemma and for overall chapter number 3, hypothesis testing. So do you have any questions so far?
Sir,
Yes.
yang untuk yang part 1 tadi tu kan, yang soalan 1,
This one.
soalan ni tapi bahagian pertama
Bahagian
kena
pertama.
memang kena tinggal
Yang mana? Yang mana?
example soalan yang ni tapi memang kena tinggal expose.
Yeah. We normally we leave as X bar lah. Tinggal X bar saja. Right. So kalau you tinggal macam ni, then susah you nak buat inference nanti, you nak calculate type 1 error and type 2 error, susah. So you tinggal lah X bar.
Okay, sir.
Others? Ada question? Ada soalan? If you don't have any question, then I think I will conclude the chapter number 3. So on next week, we're going to look at chapter number 4, which is our last chapter in mathematical statistics. So I think that's all. Thank you very much and Assalamualaikum.